What's going on, everybody? Mr. Diamond back again. And we're going to be talking now. Last time we talked about individual ions, naming things like, what if you just have a sodium that has a +1 charge? Well, that would be a sodium ion. What if you have an iron with a 3+ charge? Well, iron's in the D block, so that would be iron III, iron 3 ion. And then finally, we had negative things that were anions, and we said, what about if it was S2-, that would be a sulfide ion. We changed the ending to IDE to indicate that it is a negatively charged compound. Now we're going to look at actual chemical formulas and chemical compounds, things that are more than one atom put together other than our list of our wonderful polyatomic ions. A correctly written chemical formula must represent all of the known facts about the composition of a compound. You need to know what's in it, how much is in it. All of that information needs to be in the chemical formula that you use. Otherwise, it's not good enough. If you just say, yeah, it has like hydrogens and oxygens, that could be water, that could be hydrogen peroxide. Those are two very different things. You can drink one of them, the other one will kill you. So you have to be very, very specific. There are two compound types. Each one of them has their own set of naming rules, and we're going to talk about each one of them. There's ionic, and then there is covalent. We're going to focus on ionic today. Ionic compounds, like we talked about before, are made out of ionic bonds, so they have a metal and a nonmetal. The most important fact for making ionic compounds is that all ionic compounds must be electrically neutral, which means that they do not have a charge. Notice these three examples of them right here do not have a charge up at the top. Ionic compounds are represented by a formula unit, which shows the simplest ratio. We talked about that last time. But the whole point of making these compounds, and we did this when we made our Lewis dot structures, was we were trying to cancel out the positive charges and the negative charges. Na had an expected charge of +1. Cl has an expected charge of -1. So one Na and one Cl would cancel out and would get rid of the charge that you had. For Ca and N, there are is a +2 charge for calcium and a -3 charge for N. So if you have 3 Cas, that would be a total of +6. If you had 2 Ns, that would be -6. +6 and -6 cancel each other out. Now this last one's a little bit more complicated. Aluminum has a +3 charge. SO4 is a polyatomic, so you go to your sheet. Hopefully you have it memorized by now. SO4 is sulfate. Sulfate is a -2 charge, and there are 3 of them that we need, because then we can have -2 times 3 is -6. +3 times 2 is +6. They cancel each other out. So that is how we're going to be solving most of these questions. If it's a binary ionic compound, we just use the crisscross method, or it's called crossing your charges. Remembering that most metals have to be named using a Roman numeral, unless they're in that very small column on the one left-hand side, or if they are aluminum, zinc, cadmium, or silver. You need to have a Roman numeral. And then they're always written in their lowest possible ratio. So you wouldn't do like Na2Cl2. That's technically correct, it balances, but you could reduce that to Na and Cl. So we're going to do examples of these in a moment. I'm going to have to switch cameras, and we'll have to go to the camera where I can actually, write on stuff. But binary ionic compounds that just have two things. The examples we're going to do are iron 3 and oxygen combining together, and barium and carbon combining together. Ternary compounds, ternary means including 3 or more, and that means that they have to have one of the polyatomics in them. They're put together the same way. They're crisscross methods. You just make sure that your polyatomic stays together. You keep the polyatomic as one unit. It stays as a unit. Now I'm going to do the examples on paper here that are listed in these two questions. That's going to be in a separate video here. But I do want you to make sure that you go back, and if you want extra practice for this stuff, I have sections that are going to be back here. I just want to remind you for now that you can click through and you can test to see how good you are, or how if you want extra practice, basically. The notes are going to be here. You can go back and you can look at those questions whenever I post the PowerPoints for this. Or I guess you could freeze the video and you could try to work them out as I just clicked ahead rapidly. Either one of those is fine. But there's extra practice there. Practicing is the best thing that you're going to want to do here. For actually naming ionic compounds, so this was about making ionic compounds. For actually naming them, you first name the cation, which is positive, so it's the metal, and it comes first, which is convenient. You just name whatever the first thing is. Then you name the anion with an IDE ending, unless it's a polyatomic. If it's a polyatomic, you just leave that alone because it doesn't need to be modified. And then if it's an FP or a D block metal, you give it a Roman numeral, unless it's a zinc, silver, cadmium, or aluminum, and you just add that in the middle. You'll add that to the middle piece there. I am actually going to... I want to pause the video, but it's so much harder recording at school. I can't actually just pivot to using my recording, so we'll have to make this a separate video. This video may not make a ton of sense in this beginning context. There's just kind of a whole bunch of rules here, but watching the example video where I'll refer back to this should help quite a bit. So make sure you watch this one first and then watch that example video, and it should make a little bit more sense after that. So we're going to call it there. I want to switch over, and I got to set up the other camera. In the meantime, this is Mr. Diamond signing off. Have a great rest of your day, everybody.